Thank you very much. Can everyone hear me okay? Hope so. It's an honor and privilege to be here, and I really congratulate the Railway Board on their excellent job for this presentation and this conference. And I am hoping to really push the ball forward on this. I really appreciated what Mr. Gupta had said. And my name is Jesse Powell, Dr. Jesse Powell, and I am with Quadlev Technologies, Quadlev LLC. And what I'm proposing today is a system for 100% Make in India maglev-based system that transports passengers and freight at 500 kilometers per hour. I'll go over who we are at Quadlev, what we're proposing, and I think the overall message is this is something that can be made in India. This is the time is right to make it in India, and it really offers fantastic opportunities for all of India. But first, before I get into the details, let me give a quick preview about what I'm talking about. Here we're talking about one particular route that we were looking at between Mumbai and Hyderabad. Going an average of 500 kilometers per hour would take about 90 minutes, just a little bit over 90 minutes to get from Mumbai to Hyderabad or back the other way. The key to Quadlev and implementing all that maglev technologies have to offer is to sustain massive throughput. If you can keep your throughput as high as possible, lots of things become possible. We're looking at a full capacity of 394,000 passengers a day on a single two-way guideway and over 500 billion net ton kilometers of freight per year. And this is something that we believe is profitable and ideal for a public-private partnership. Now again, this approach can be applied to any other route in the country, but we took this route because we really think it showcases the long-term economic development possibilities when you really start to think about what can we accomplish with maglev. So a little bit about who we are. Quadlev is a new company and a new brand, but we have a long history in maglev technology development. Our founders, Gordon Danby and James Powell, Jim Powell's my dad, invented maglev, invented superconducting maglev. Their version of superconducting maglev is the version that is running in Japan today. We have a number of partners, including Maglev 2000, which was the company formed by Danby and Powell to do the research and development and the prototype building for the second generation of maglev, which really hasn't become noticed on the world stage yet, but will for reasons that I'll go into. Another partner is Readiness Resource Group. They're a specialist in government contracting and working to implement and manage large projects. Maglev Strategies is a consulting firm to explain how maglev works and how to implement maglev programs. We offer teaming with industry and government. We invented first generation maglev, second generation maglev, and now we're working on a third generation of maglev technologies. We offer consulting services in tech transfer, research development, test and evaluation. So there's a lot of misconceptions about what maglev is. And people think it's a very complicated technology, but you have to take a step back and think about the core essence of what maglev is. It's really just an empty box with some magnets stuck to the side. It sounds too good to be true, but that's all a maglev vehicle is when you come right down to it. So here we have an empty box, and in purple you see the superconducting loops that create the magnets. There's no moving parts in a maglev vehicle except for landing gear when it comes into the station and has to sit down somewhere. There's no complex controls because the vehicle itself doesn't determine where it goes. The guideway tells the vehicle where to go. It's very low maintenance. There's no physical contact between the vehicle and the guideway, so there's actually no physical wear and tear. The magnets themselves can last a very long time. We're looking at components that have mean times before failures of about 1 million hours. So it's gonna have very low operational costs. And overall, we think the cost of superconducting maglev is going to be cheaper than steel wheel rail, not too far in the future. So we talked about a vehicle. What is a guideway? A guideway is just a concrete beam with some simple metal loops in it. Some of these loops are connected to AC power. Some of the loops are just closed metal loops that are embedded in the concrete that create the magnetic fields for levitation and stabilization when the vehicle passes over it. Again, very low maintenance because there's no contact, very low cost. Everything in our quad-lev guideway design is pre-manufactured in factories, shipped to the site, and assembled in place. So there's very little custom construction that is necessary. This allows you to deploy maglev very quickly at very low cost. Why is superconducting maglev going to become game-changing? You look at the cost of high-temperature superconductors. It's following the same cost dynamics as solar power. A couple years ago, people were saying solar power will never be a large player in power generation. It's never going to displace coal. And now today, we have coal plants all over the world shutting down because it's cheaper to generate power with solar power. The same thing is going to happen with high-temperature superconductors. When we first started building our second generation magnets back in the year 2000, the costs for high-temperature superconductors would have been about $30 million per vehicle. Today, it's down to less than $1.5 million per vehicle. Within 10 years, we believe it's going to be down to $200,000 or $300,000 per vehicle. And when you think about it, a maglev vehicle is just a box with some magnets. They're lighter weight than rolling stock, and there's no maintenance involved with them. So again, we think that maglev is going to be the future. Maglev is not some far-off technology that's always off in the future. You can buy it today. Japan would be happy to sell you their maglev system, I'm sure. They have an excellent passenger-only maglev, superconducting maglev system. They're building between Tokyo and Nagoya and now Osaka. And they have a multi-decade research and development testing and evaluation program to back up the principles of maglev, which are based on the original inventions of Powell and Danby. Not all maglevs are equal. One of the reasons we chose the name quad-lev is because now everybody associates maglev with all sorts of different things, and it gets very confusing what we're actually talking about. There's electromagnetic maglev, that's what transrapid is. There's permanent magnet maglev, that's basically the approach that I believe Hyperloop has taken. And then there's superconducting maglev. And if you look at all the features that are desirable in a very high-speed transportation system, large levitation gaps, strong stabilization forces, the ability to carry heavy freight, high-speed switching, these are all really advantages of superconducting maglev. We have the lowest system cost, and I'll get into reasons why. And so I've been watching the Indian press for the last 2 weeks, and I've seen a lot of stories about Hyperloop, and the stories inevitably go, Hyperloop is the future, maglev is old and too expensive, and Hyperloop is going to be cheaper. I'd just like to point out that the principle of operation of Hyperloop is you take a maglev vehicle and you put it in a vacuum tube. And so basically it's maglev in a tube. So if somebody could tell me how you can build a maglev system with a complicated vacuum tube system that has all the engineering associated with that for cheaper than you could build maglev alone, I'd be interested to hear that. Secondly, the basic concept has been around for a long time. Maglev in a tube has been proposed going back to 1914. Before that, it was pneumatic transport in a tube. It's been looked at and patented in the US many times. We looked at it. We had something called Mach 3 maglev, which went not 1,000 kilometers per hour, but 3,000 kilometers per hour, Rand Corporation, Swiss Metro. Going fast in a tube is not hard. Going fast around curves is hard. Going fast and having high-speed switching is hard. There's a lot of engineering challenges associated with that. Hyperloop, either of the Hyperloop companies may be able to overcome those challenges, but we bet it's going to be a lot more expensive than they think it is. That being said, there's a number of really important questions that travel in evacuated tubes has to answer before anybody starts putting serious development money into it. What is the levitation gap? What is the levitation gap when you're carrying freight like 25 or 50 tons? If you're only having a levitation gap of 1 centimeter and then you're going at 1,000 kilometers per hour, you're going to go basically in a straight line. Does it have high-speed switching? What's the use of going fast if you can't maintain your throughput for your entire network, if you have to slow way down for switching? Does it handle container freight? What are the tube construction tolerances? One of the disadvantages of electromagnetic maglev, the transrapid system, was because they had a 1 centimeter tolerance or levitation gap, they had to make their guideway very, very precise, and that added cost to the overall system. From a safety perspective, how does emergency braking work? You want to have multiply redundant systems. One of the best ways in an open air superconducting maglev system is you just put up air flaps. You slow down very quickly. Can't do that in a tube where there's no air. What happens if a pod depressurizes? In an aircraft, in an airliner, when you're taking a jet airplane and the airline depressurizes, you possibly will pass out. If you're traveling in a tube that has 1/1000th the atmospheric pressure, it's like taking your helmet off in space. It's not going to be a good day. What will happen if the tube catastrophically fails and there's a repressurization event? My understanding of what will happen is you'll get a supersonic pressure wave going down the entire tube. That's going to be a bad day for the vehicles in the tube. These are real engineering challenges that need to be met. They're going to be met they can possibly be met, but only with great expense. And there's always going to be the safety factor to consider. We think we have a better approach. What we're doing is we're taking all the advantages of superconducting maglev and putting them together in an integrated system. We carry heavy freight. We have multiple guideway configurations possible, and I'll explain why, but we can travel on elevated, narrow beam monorail type guideways, but we can also travel on flat planar guideways. We use prefab construction. Our vehicles can travel either individually or in multi-vehicle train sets. This is an advantage where you can actually provide service at the level that you need it. And we have high-speed switching. We try to keep our main guideway just for high-speed operations and then have all vehicles switch via high-speed switching to offline stations. This keeps the average speed very high. And then finally, we can power this with renewable energy. We don't need fossil fuels. A little word about magnet design. The first generation maglev systems, such as used in Japan, are basically dipole magnets. All that is a loop of superconductor carrying current. So long as you keep the superconductor cold, it will carry the current forever, effectively. What we've done is we've taken a second dipole and put it right next to the first and run the current in the opposite direction. This is called a quadrupole. Now, if you look at the lower panel with the sectional view, through the dipole, you only have one face that you can actually interact with. With the quadrupole, you can have 4 faces that you can interact with the magnetic field on. This allows us to travel on multiple guideways. Quadrupole is also advantageous because it has a 5-fold lower magnetic field away from the magnet. If you're a couple meters away from the magnet, the fields you experience as a passenger are 5-fold less with quadrupoles. So again, our quadrupole magnet design makes it possible to use multi-guideway operations, carry heavy freight, and do high-speed switching. We built prototypes, we designed them, built them, tested them, and patented them in the US. And originally we built them with low temperature superconductors, which is a lot harder to do than with high temperature superconductors. And now that the cost has come down for high temperature, we're adapting it to high temperature. Why freight? Because that's where the money is. That's where most of the revenues are. You use freight service to cross-subsidize passenger fares. You all know that here at India Railways. Most passenger-only systems in the world are loss-making. So you want to carry freight to subsidize your passengers. Furthermore, we believe the quad-lev approach is going to dramatically lower logistics and transportation costs. India has amongst the highest logistics costs in the world for a country its size. What if you could slash those in half? What would that mean for India exports and industry? So we try to bring this all together into a universal transport solution. We have massive throughput. We have 3-minute headways between vehicles, offline stations with high-speed switching. So on that main guideway, you're going to see cars going by every 3 minutes, whether they're single cars or multi-vehicle train sets. That guideway is going to be occupied all the time. We carry passenger and freight. Why build 3 different infrastructures, commuter rail, freight rail, and high-speed rail, when you can build one infrastructure? No ongoing government subsidies. We think this is going to be profitable from almost the very start. Single or multi-vehicle operations, as I said, you can balance total system capacity or throughput versus scheduling freedom. If you're building up a train set of 100 cargo wagons, but one of those wagons is really high priority, you don't have to wait for the locomotive to get the whole train set together. You can just send that one off by itself. And then another unappreciated aspect is dynamic network optimization. At maximum capacity, a single 2-way guideway is going to be carrying tens of thousands of cars a day. And they're all going to be changing scheduling based on needs and priority and congestion pricing. This is something that can only be handled by algorithmic allocation of assets. So whenever you have demand is high over here, but supply is high over here, you move all your vehicles over there automatically. This is great for responding to emergency situations. When you have a huge increase in transport demand, like at a harvest, there's all sorts of reasons for this. Safety. Maglev is going to be a lot safer than conventional rail in the long term. The reasons for this are the physics of maglev. Collisions are nearly impossible. Basically, the maglev vehicle is stuck at the speed it travels according to the guideway. The speed is set by the AC frequency in the guideway. So as soon as you have one vehicle trying to overtake a second vehicle, it enters into the same section of energized guideway, and they are locked into the same speed. There's no way they can overtake each other. It's very hard to derail a maglev vehicle. With rail, all you have is gravity holding the wagon to the track. With maglev, there's a set equilibrium point where the vehicle wants to be, and anytime there's a force that pushes it away from that, there's a restoring magnetic force that arises automatically, passively, but strongly, to restore it to its equilibrium point. So we're looking at lateral accelerations for the monorail configuration of 5 Gs. For the planar, lateral accelerations of 1 G. That's way higher than you're ever going to want to put your passengers through, believe me. Unless they're really into jet fighter experiences, you're never going to get there. Compare this to conventional rail, 0.1 G, 0.2 G is where you're stuck at. So these aren't going to derail. Energy efficiency. We have no contact with the ground, therefore we don't lose any energy to friction, to ground-based friction. We think overall, compared to high-speed rail, we're going to use about 1/3 the energy of high-speed rail. For freight, we think we can transport freight at about 40% the energy of conventional freight. And this is what makes it possible to power the whole system with solar power or wind power. So this is just the example line that we looked at. 800 route kilometers. We're looking at a public-private partnership, but this is all in flux. We're working with people in the ministry and people in industry to figure out what works best for everybody. One end of this route connects directly to the port in Mumbai. It follows existing rail lines for the most part, so you don't have to spend a lot of money on land acquisition. And the best part is because our approach gives you so much massive throughput and capacity at maximum capacity, if we start out at 10% capacity, we can grow for 25 years at 10% compound growth. That is an enormous opportunity for economic growth for the entire region and for all of India. So again, these are all initial models. We start out at 10% capacity, and with 25 kilometers of headway between trains, we think we can run basically 960 trains a day on this two-way guideway, half of them as passenger trains and half of them as freight trains. Freight trains could have up to 100 separate wagons, and passenger trains could have 10 wagons, but you can mix and match this as need arises. So again, maximum throughput of 384,000 passengers a day, and you could transport 96,000 containers or roll-on, roll-off trucking. That's another advantage of our approach. We realized in the United States that because most of the freight revenues comes from trucking, if we can roll trucks onto the vehicle, transport them at 500 kilometers per hour, and then roll them off, everybody wins. The trucking companies win, the rail wins, and the country wins. Our network fare model is open to adjustment, but we're looking at 90% of our revenues from freight and comparable fare prices to high-speed rail for passengers. But because we're getting most of our money from freight, we can lower those fare passengers even further, and we're profitable. Financing, these are all preliminary numbers, but we're looking at an overnight CapEx cost of 90,000 crore, looking at 25-year loans. We think we can make this profitable from the very beginning. I'm rushing because I know I'm running out of time, but thank you. Now here is the real winning point of this. You know that economic development is centered around logistics and creating smart corridors of logistics. This is what will get us there. With maglev-oriented development, we can create an entire corridor connecting two major cities like Mumbai and Hyderabad. And then we can develop the entire intervening space. With 25 years of capacity growth, imagine all the opportunities this brings. Then finally, and most importantly, by the year 2050, the world is going to spend $165 trillion on infrastructure, transportation infrastructure. Why not get in on that game? Right now, maglev is an emerging industry, and nobody is leading it. India has everything it needs to really lead this industry, and that could translate into large export revenues just a little bit down the line. So Quadlev is working with some Indian partners right now, and we're putting together a coalition or a consortium, and we're happy to talk to anybody, and thank you very much. I'll take any questions anybody has.